Our next speaker is Graeme Stewart, and he will talk about jet finding in Julia. Go ahead, Graeme.
Yeah, okay, thanks very much. Yeah, let me start by giving a bit of an overview of this talk. Why was it that we did this work? Because we can find jets at the LHC. There's a very good package for doing so. But we were actually quite interested in, as we were sort of starting to think about Julia, understanding a little bit the process by which that would happen in terms of how does it look and feel, how does it feel to develop inside of Julia, and at the same time also to check that we can reach the algorithmic performance of current algorithms that we have in C++ as well. And yeah, I think the first part of this slide, Jim covered all of that on Monday, the fact that we've ended up in the C++ Pythonic environment, but Julia looks a hopeful way to get out of that kind of conundrum. So yeah, we wanted to pick then a problem that would be interesting to investigate, and jet finding is one of these. We were picking something because if you look at the benchmark stuff, it's stuff that's just benchmarks. It doesn't tell you how it's going to perform on real world problems. And jet finding is a nice example of something in CHEP which is not so simple that it doesn't add much to kind of general metric that you might do. But it's not so complicated that it takes you a very long time to implement as well. So in a certain sense, it was just kind of Goldilocks algorithm. It's not too hard, but it's not too easy either. The problem, I think, is probably familiar to many people in the room. At the LHC, of course, well, actually in general in particle physics, you have a high energy particle, comes into the calorimeter, it undergoes a showering process where it breaks apart into lots of child particles. And then the inverse of that problem, of course, is to reassemble all of these children of the jet and cluster them back so that you recover the energy of the incoming primary particle, which is what you're really interested in. So you kind of have this splurge of particles in a calorimeter here, and the colors are what you would get out from the jet reconstruction, essentially, that you've clustered all of these things together in the most appropriate way. The algorithm which is used mostly at the LHC, is called anti-KT clustering. It's used by the FastJet team because it's infrared and collinear safe. So that basically means as we move to higher pile up at the LHC, these algorithms are robust against adding more soft radiation into the problem. So let me just briefly describe what the algorithm is. I mean, the first essentially that you do is you define a geometric cone, and this is the region in which you're going to consider that you can reassemble particles. So this cone size type of parameter, 0.4 is typically used at the LHC. 1 is also used as well for other cases. And then for each of the particles that I'm currently considering, I then measure the geometric distance to all of the other particles, and I find the minimum of that. So I'm saying, okay, what's the closest particle to me, as long as there's something inside of R. Otherwise, I set the distance to R. So that's the geometric distance, but then I define a metric distance that also depends on the transverse momentum of the particles as well, and that's done as in this 211 thing, which is here. Okay, so you essentially weight this by the minimum of one of the jet PTs. What's key to the algorithm is what power of P you use at this stage, and when you pick P equals -1, this is where you get the anti-KT clustering algorithm. Other choices that have been used historically in particle physics are P equals 0 and P equals 1. But P equals -1 essentially favors merging high PT particles first of all, and this is what makes it robust against the soft radiation, because you do all of the high energy pieces, and then only then do you sort of cluster in the lowest energy particles as well. Okay, so you do all of that, then you pick the jet that has the lowest value of this metric distance, and if it has an active partner, so if you found another particle close by, then you merge these two. Okay, and if not, then this is a finalized jet. So once there's nothing else that you can merge, this is my jet, and you keep on doing this until you have nothing left after all. Okay, so this is quite a nice algorithm actually, because you can see that this part here, because I'm doing lots of jets in parallel and they don't depend on one another, I have parallelization opportunities which exist there. But this bit here, step number 3, I have to find the global minimum. So naively, this piece is serial, but as we'll see, it's serial-ish, because there are some tricks that you can do to accelerate the calculation, which we've discovered. Okay, and then you in the end, you end up with something like this, you know, where you have these different jets covering different areas as well. I think that diagram is from the original FastJet paper. Okay, very good. So on top of that, because the algorithm is determined by the value of P, you then have different strategic implementations of the algorithm as well. And we've implemented 2 of these. The first one is the plain vanilla version, where you essentially just consider a global space of particles. You don't bother splitting things up at all. And you have a global pool of jets, and this is the one that Attell did last year when we were working with him. And then there's a tiled version of the algorithm as well, which was originally introduced by the FastJet team. And here the idea is that you split your plane in rapidity and phi up into these little boxes, which have the width of the radius. And the idea behind that is that if I have a particle which is here, then I only need to care about particles which are in the blue boxes there. So I'm reducing the amount of work that I'm doing because of the tiling. So Philippe did the original implementation of this one in Julia as well. So you have 2 situations. The tiling algorithm or tiling strategy, I should have said, involves more bookkeeping, but it reduces the total amount of work that you need to do. The basic strategy does more calculations, but these are somehow more amenable to parallelization because everything is uniform, everything is the same. So what are the implementations that we were looking at? So obviously the C++ FastJet package is very much the reference implementation. It's used ubiquitously inside of high energy physics. We wanted to look at Julia, clearly, so we did that one as well. But of course, given the prevalence of Python, we thought, well, maybe it's interesting. Let's try this in Python. We'll try it in pure Python, pretty much as an academic exercise. But one is, you know, but you're testing the ergonomics here. You're not expecting it to run fast, but you're saying, okay, from a programmer's point of view, I sit down at my laptop and I type some code. How easy is it to get the code to do what I actually want to do inside of the algorithm? And then the classic thing to do inside of Python is then to try and accelerate this with NumPy and Numba. So we'll do that as well and see how much does that change your experience as a coder. And the initial results we presented at the CHEP 23 conference earlier this year in May, and these were the results that we got. So first of all, just to say that these are benchmarks which are taken essentially against LHC events. These are 13 TeV PP collisions. The benchmark number of 1 here is determined by FastJet using the tiled strategy, and that on the machine that we were testing on, that came out at 324 microseconds per event. There's very little jitter on this. I mean, everything runs very reproducibly as well. And we did not include the time to read the events from HEP-MC3 format or the time to JIT for Numba and Julia. So we're really measuring the runtime of the algorithm once everything's been prepared. And you can see that for the plain algorithm here, actually the best implementation was the one in Julia. It was significantly faster than the implementation in FastJet. Python was terrible, as expected. Accelerated Python was also surprisingly terrible. The reason being that although you can accelerate quite a few of the calculations, a lot of the bookkeeping has to be done in bog standard Python inside of a for loop, and that starts to become dominant in the runtime. For the tiled implementation, which we of course expected to be much faster, FastJet was indeed the best. Julia came extremely close. It was a 12% off, but you know, that's pretty good result, actually. Pure Python was quite a bit faster when you use the tiled implementation, gets about a 4-factor speed up. Accelerated Python is a disaster here because you have this competition in the tiled. You're deliberately reducing the amount of work which is actually done. And that means that the advantage of using Numba and NumPy shrinks away to nothing. And then you're just left with this much more complicated bookkeeping, which is still in pure Python. So it takes even longer. So this was really awful here. Yeah, the Python implementations were not competitive. I'm not claiming that you couldn't do better. I mean, probably you could, but you know, starting from here, the idea that you would get it down to where Julia and C++ are is quite fanciful. Okay, so yeah, I mean, and the comment is also that the ergonomics of the accelerated Python were painful, honestly. And we looked into why the N2 plane algorithm in Julia was so good. And that we understood that it was actually because we used the structure of arrays layout there. So the memory accesses were so much quicker than that. And things like SIMD optimizations could be applied by the compiler as well. So this was looking pretty good. I'd say this was a great result for Julia. This is what made me think, oh, I should really do more Julia, shouldn't I? It's really good. Okay. So a few comments on the ergonomics. I mean, the FastJet code is pretty good code for C++. Actually, it's sort of C++, it's sort of C, really, because it's fast because it uses C type of data structures and it uses fast, tight for loops inside of C. It's pretty well written code. I can't criticize the authors for the way in which they wrote the code, but there's definitely some tricky parts because you have these arrays of arrays. So you have pointers pointing at pointers, and that's just hard to reason about to make sure that you're really doing the right thing. It also makes it difficult to guarantee the data structure consistency when you're using things like linked lists. You have to be very careful in the way that you update these things. But okay, fine, it is what it is, and it runs fast, so can't blame those guys. Python, yeah, the pure Python code was very easy to reason about and to use, so it was a sort of very pleasant programming experience. Obviously, the runtime was disappointing. As I already mentioned, the NumPy Numba accelerated code was hard because you need to cast the problem into this NumPy array layouts. And if you think about the algorithm, it doesn't really naturally fit into array structures. You know, it's a particle thing there. And actually, the Numba acceleration was a bit disappointing because it didn't work for a surprising number of things, like basic functions like wrangling 2D arrays into 1D arrays wasn't supported, so I had to write that by hand. So that was a bit painful. The experience of Julia was pretty pleasant. So it was as easy as pure Python for the basic implementation parts. It was particularly nice to be able to use the broadcast syntax for being able to calculate initial values of things. It's compact, easy to understand. In the C++ case, it is essentially using the same kind of implementation as C++. So the code has some look and feel, which is the same, but it doesn't have pointers, so it does make reasoning and safety about the code that bit better. So nice. Okay, it was a good experience that we had there. Then okay, so we got so far with it. Could we improve it further? So after CHEP, we profiled the codes again, and I realized that there was a rather significant amount of time was being spent in that step 3 where you were finding the minimum value of this metric parameter across all of the active jets. Now, when you think about it, you realize, oh, yeah, but actually I can do this in parallel because I can split this array up, find the minimum in each piece of the array, and then compare the minima together. So I can do a divide and conquer approach here. So maybe there's an easy way to do that inside of Julia. And once I realized that you could do that, the actual searching itself is quite straightforward. We did have a conditional in there, you know, is this lower than the minimum that I have already found? It was easy enough to write that as a ternary operator, which loop vectorization can digest. And then you can apply the turbo macro from loop vectorization. So that's the code here. It's pretty straightforward, as long as you remember what the ternary operator does. Sometimes I get confused when I haven't used it for a few months. Wait, is it colon question mark or is it question mark colon? But, you know, when you see it, it's fine. Interestingly, you know, Atel was saying, you know, but there are these sort of minimum finders in Julia. This is 5 times faster than findmin, actually. So it's very significant for this problem to take 28 microseconds instead of 131 microseconds. You know, typically you're dealing with sort of 400 to 500 particles, and then the array is shrinking by 1 each time. So you're kind of going from 450 down to 1 in the end. So this was a very nice speed up. Yeah. I had a go at implementing other algorithms as well. So given that the use of structure of arrays was pretty successful in the plane case, I wanted to see if we could adapt to something similar in the tiled case. I had 2 goes at doing this. One was to implement a structure of arrays in each of the tiles so that I could do fast calculations on these structures. Wow, that was slow. That was hard. And the problem was that when you set up the tiling, you've then got to set up containers to put my jets in there. I've got 500 tiles and I've only got 200 microseconds. So even when you're like assigning one object is quite fast, times 500 times each of the different arrays that I need for the structure of arrays. So you basically blow the budget just on allocating the structures because you don't have much time to do this per event. So that wasn't a winner. Then I tried, okay, maybe I could have a global structure of arrays for all of the jets. So I could make certain global calculations a little bit faster. This turned out to be faster than my first attempt, for sure, but it was still slower than the original linked list used in the N2 tiles. And the reason is that the tiled algorithm is just so successful at shrinking the amount of work that there are very few places where you actually ever do a calculation on the global array list. So the SOA doesn't really buy you much in the end. So yeah, I think hats off to the FastJet people. They found it really the best way of doing this. Although we re-implemented that inside of Julia. I have to say that ergonomically working with SOA was really difficult, but I didn't know about struct arrays. Back in those days, this is what, you know, what you do, you know, you come across a new ecosystem and you don't know everything. So if I was to redo it today, it would be a lot easier to work with, but I doubt it would be any faster in the end. For posterity, these things are preserved in GitHub if anybody wants to go and have a look at them, you know, but they've been removed from the actual code nowadays. Okay, so what's the current performance? So benchmarking on the same set of events that we used at HEP, that's 413 is the average particle density. So we dug out Pythia 8 and we generated lots of other sets of events. So these range from E plus E minus at the Z pole all the way up to some like high intensity 30 TeV PP collisions as well, just so that we get realistic events. You can't really just take PowerPoints and spread them all over the place because that's not what events look like. You've got to use an event generator. And we also threw in a few heavy ion events just for laughs. So there's some backup slides there that I might go through if we have time. Okay, so what are the results? So this is the two algorithms, sorry, two strategies in Julia. This is also anti-KT. I have to say, we've also done the Cambridge-Aachen and the inclusive KT, and it basically makes no difference to the runtime because it's just a different power, but the algorithm itself is stable. You get better physics results from the anti-KT, which is why you want to keep trying that one. So you can see that these things scale, they have very different scaling with the number of particles, so that the tiled algorithm really is good at keeping the amount of work that needs to be done down, whereas the plane algorithm, yeah, very much N2, because it's sort of N squared type of algorithm. However, once you get down to E plus E minus densities of particles, the plane algorithm is actually faster. So at the Z pole, it's 37% faster. And for E plus E minus at the Higgs, energy is 25% faster. But it's very, very quick. I mean, you're down at about 10 microseconds per event here. This is really fast to reconstruct jets at these low densities of particles. So good, that's the Julia results. So you would want to use the plane algorithm down at E plus E minus. At the LHC, you definitely want to stick to the tiled algorithm there. Comparing to FastJet, so this is the plane algorithm. As I already pointed out, we understood that this was performing very well because of the structure of arrays layout. And the loop vectorization that we actually also applied to. I did this 2 days ago, by the way. I discovered that the loop vectorization worked for this strategy as well. But it's still it's a bit faster at the Z pole, so you gain a little bit over FastJet. Then of course it scales much better. But to be fair to FastJet, I mean, you just wouldn't use this algorithm, this strategy at high density. So why would you bother spending a lot of time optimizing it? So I don't think they can be criticized for that, really. Turning to the tiled algorithm, we do see a measurable advantage actually for Julia at the higher particle densities. This obviously grows with density because the advantage of doing this accelerated Dij finding, the longer your array is, the better. So the codes are pretty good. Of course, certainly Julia matches and indeed even beats slightly the C++ speed. I mean, there's a little bit of a weird thing which is going on, is that without this Dij acceleration, Julia is actually a little bit slower. And we would quite like to understand that, but we're also kind of à la limite in terms of, you're very much doing detailed optimizations. And somehow the advantage of Julia is that you don't have to dig into every single last 0.5%, although it would be nice to have an understanding of why that would be the case. But yeah, I mean, very happy with this result for sure. All right, so I think we feel that the Julia version here is certainly fast enough to merit being released. The caveat is it's only a small amount of what FastJet does in terms of lines of code and methods. That although the rejoinder to that is in fact that the thing that we've implemented is the thing that 90% of people actually want to do. So it's probably still worth it, even if it's not the total coverage of what FastJet is, because it's a big package and it's been around for a long time. So we needed to, because the implementations had been done independently, we tried to make them more uniform as well. So we now have this as kind of the interface that you have. You have this tiled JetReconstruct. You provide a vector of particles of some type T. The P parameter determines the algorithm. The R parameter is the cone parameter. You can also say how to combine these particles as well. So you can pass in a function, or for your type T, you can, the default is always just to add the 4 vectors. But if you want to do something fancier, you can do something fancier. And you're allowed to put in a cut as well on PT, and then I only bother to send you back the jets that you're interested in. I think one place where Julia is super nice is that for this type T that you pass in, you pass whatever you like, as long as I can work with it as a jet, right? Then it's absolutely fine. So you have some funky class that you're using for your particles. As long as I can look at it as a jet, I'm fine, so this is a really nice thing. In FastJet, it's actually templated, but then you would have to recompile FastJet against your type. Whereas in Julia, you just go use it, which is great. And at the moment, we know that this works absolutely fine for Lorentz vector HEP and for this pseudo-jet class that we use ourselves, because that's the one that we actually use internally. And we've improved the testing against anti-KT and Cambridge Athens. So we get exactly the same results as FastJet as we should. Okay, things which haven't been done. Oh God, documentation. Yeah, I mean, we have a better README, but we need to do proper documentation if we actually want to release it. There's a few inconsistencies with the way that we return the sequence merging history. So I think we should go for the FastJet one, because that's the one that people are used to working with. And there's a little optimization that we need to do with the pseudo-jet class, because at the moment it has a data member which is strictly speaking internal to the implementation, but that should be easy enough to remove. We now know basically how to do a best strategy, so the user shouldn't have to define what the strategy is. We should just look at the number of particles they've got and pick the appropriate one. And the plotting backend that Attell did was really nice, and then I broke it because I changed some things, so we should fix that. We should fix that too. So yeah, it looks pretty good. So conclusions are that jet finding was a really good example to try in Julia. The performance in the end, it was somewhat better than FastJet, which is known to be highly optimized. The programmer experience of using Julia was lovely. The fact that there's no pointers, better memory safety, easier to reason about the code, much easier to profile. So when we were looking at the performance, trying to find out, wait, why is this slower than I expect it to be, was really easy inside of Julia with the flame graph type of stuff. Very easy to apply optimizations via macros. I think this is just an amazing feature of the language. I find a piece of code, I want to optimize it. I don't change my code, I just add a macro. Wow, it's gone. Tooling for debugging was really good. And definitely more flexible for people who actually want to use the package to inject their own data types. So the release of the package is rather close now, although I think it's sort of zooming out again, it would definitely be a good idea to release a version of FastJet that can be used inside of Julia as well, because there's a lot of functionality there. So depending on your use case, you might want to go to FastJet. And people trust FastJet, actually. That's another thing. Yeah, that's basically it.